Hi everyone. Welcome to EasyTech Masters online series. If you are watching this video for the first time, kindly subscribe this channel, share this channel, and click on the bell button for more videos. And today's in this video, I want to describe testing of transformer. Yes. The first question we may ask: why we need the testing of transform, why it is required to test the transform. So I will give the answer for these questions. That is, the first one is why we test the transformer. We test transformer. And the second one is what are the various types of tests. What are the various types of tests? Various types of tests that are available to test the transformer. Yes, if we see the first question, why we test the transformer? So tell me, why we test the transformer? Because we know the transformer. What do you mean by transformer? Transformer is the static device. Transformer is static device. Yes, this static device, or we can also say it is the static electrical machine which can transform electrical energy from one form to another form. From one form to another form without changing in frequency. That means frequency is kept constant. Frequency is kept constant. This is about transformer. That is what the transformer will do. Transformer is a static device which can transform the electrical energy from one level to another level without change in transformer. For such transformer, how we test, how we perform the test, and what is the basic criterion to test the transformer. Generally, we used to conduct the examination for the students. Why it is? Because in order to know the performance of the student. So here also the same criterion we follow for the transformer. That is, to determine the performance of the transformer, we conduct the testing. What are the performance index of the transformer? There are two parameters are there for the performance. What are the two parameters in the sense? The first one is, the first one is losses, and second one losses and hence efficiency. Losses and hence efficiency. And the second one is regulation. Regulation. Yes, losses and hence efficiency. That means the first parameter is efficiency. Efficiency must be high value. The regulation must be low value. Regulation must be low value. So how we find out the efficiency? This what do you mean by efficiency? Efficiency is the ratio of output power to the input power. And we know that in the transformer is a static device which transforms the energy from one level to another level without change in frequency. And in general, in ideal case, we consider the transformer as it is a constant power device. That means how much power we are giving at the input, the same amount of power we used to get at the output also. That means ideally the efficiency of transformer is 100%. But practically it is not 100%. Practically it is not 100%. So the efficiency may be low, maybe decrease. So due to the presence of winding or due to the presence of core in the transformer. So here that whatever may be the parameter which cause to decrease the efficiency of the transformer is to be considered as the losses in the transformer. Therefore, now I am going to tell about losses in the transformer. Losses in transformer. What are the various types of losses that are available in the transformers? Just tell me, what are the various types of losses are there? There are only two types of losses are there. Those are, the first one is electrical losses. Electrical losses. And the second one is magnetic losses. Magnetic losses. Yes, what do you mean by electrical losses? Electrical losses in the sense which are also called winding losses. Which are also called winding losses. Yes, what do you mean by this winding losses? Wherever winding is there, that means winding in the sense we represent the winding like this. Wherever winding is there, this equivalent of this winding is, it is the combination of resistance and inductance. That means winding in the sense it is not pure inductor and it is not pure resistor. It is the combination of both resistor and inductor. So whenever the current passing through this coil or through this winding, then what happened? The current is passing through the resistor also. Current is passing through the resistor also. Whenever the current is passing through the resistor, what is the property of resistor? Resistor will oppose the flow of current. Oppose the flow of current. And second property is the resistor will drops the voltage. That means voltage will be drop at the resistor. Okay. Then what about the power? Power will be absorbed. Power will be absorbed. Then what about energy? Energy will be dissipated in the form of heat. In the form of heat. So now we consider these four statements. What the resistor will do? Resistor will oppose the flow of current. So whenever the current is passing through the resistor, that resistor will drops the voltage. Whenever the current is passing through the resistor, then resistor will absorb the power. Whenever the current is passing through the resistor will dissipate the electrical energy and electrical energy into the form of heat. Into the form of heat. So now let us we consider this one, that is power. What the power? What about the power? The power will be absorbed. Power will be absorbed. So power will be absorbed in the sense that much amount of power is wasted, which is to be considered as loss of the transformer, loss in the winding or loss in the resistor. This loss is given by the power in the resistor is P is equal to VI. From the Ohm's law, if you apply, what is Ohm's law? V is equal to IR. Therefore, IR times I. So hence it is I square R. I square. So this power is depending on the square of the current. Power is depending on the square because we cannot change the value of resistance. Resistance is constant. If you take any winding, for that winding the resistance value is constant, and which will be varying in the sense current is changing. As current is changing, the power loss is also changing. So therefore here electrical loss is also called winding loss, is also called copper loss, which is to be treated as variable losses. Which is to be treated as variable losses. Okay. Suppose for example, the transformer contains the full load copper loss as WCUFL. Now I want to find out what is the loss at nth load. At nth load. Suppose at full load I have 500 watts. Now then what about the copper loss at half load? At half load, how much copper loss will be there? Can I write 500 by 2? No, I do not. Here I need to write 1 by 2 whole square into 500. So that means if the copper loss at full load is WCUFL and the copper loss at nth load is, yes, how much it is? N square into WCUFL. This is how we can find the copper loss at any load if I know the copper loss at full load. If I know the copper loss at full load. Okay. Therefore, electrical losses or copper losses are the variable loss. Okay. Next, the second losses are magnetic loss. Magnetic loss. Yes, what do you mean by magnetic loss? Yes, what is magnetic loss? Magnetic loss in the sense the loss which occurred in the magnetic circuit or the loss which occurred in the core of the transformer. There are two types of the loss, magnetic losses, which are called hysteresis loss and second one is eddy current loss. Hysteresis loss and eddy current loss. Okay. So as this loss is occurred in the core of the transformer, therefore it is also called core loss. Once we fix the core, once we decide to establish the core for the transformer, the loss is also fixed. The loss is also fixed. For such core, the loss may be the constant. Therefore, this loss is also called constant loss. This loss is also called constant loss. And these two losses are depending on the frequency. How it is in the sense, hysteresis loss is directly proportional to frequency and eddy current loss is directly proportional to square of the frequency. Square of the frequency. That means here, if I know the hysteresis loss, that is, let me assume WH1 directly proportional to F1 and WH2 is directly proportional to F2. So hence from this two I can write WH1 by WH2 is equal to F1 by F2. If we know any three values, then we can find the unknown value. Unknown, that is the fourth value. And next one is WE1, eddy current loss, is directly proportional to F1 square. WE2 is directly proportional to F2 square. Okay. So therefore WE1 by WE2 is equal to F1 square by F2 square. Okay. It is not mandatory that the eddy current loss at some frequencies this and so like this. But we cannot say the same amount of loss is there for the hysteresis loss. Because if you see, the equations are different. Equations are different. So hence, I used to write the core loss as, which is also called iron loss, that is equal to hysteresis loss plus eddy current loss. This is K1 into F plus some K2 into F square. K2 into F square. That is the iron loss of the transformer is the function of frequency, and this function is the quadratic function. Quadratic function, and this equation is quadratic equation. Quadratic equation. Yeah, this is how we have the loss in the transformer. That is eddy current loss, hysteresis loss, which are belongs to the iron loss, and next one is copper loss, that is electrical losses or winding losses or rheostatic losses or resistive losses or variable losses. Okay, and we do you know the efficiency is maximum when it is maximum in the sense when Wi is equal to Wcu. That means the constant loss is equal to variable loss. Whenever this constant loss is equal to variable loss, then the efficiency of the transformer is maximum. Efficiency of the transformer is maximum. Okay, now how we find these two losses from the testing of the transformer? Yes, before that, what are the various types of tests that are available to test the transformer? In the sense, let us see. Basically, there are two types of tests. There are two tests are available. Those are, the first one is open circuit test. Second one is short circuit test. Open circuit test, short circuit test. Open circuit test. First let us see open circuit test. Open circuit test. Yeah, the first one is why we are conducting the open circuit test. This open circuit test is conducting to know the no load loss of the transformer. The no load loss in the sense constant loss, which is also called iron loss of the transformer. That is, with the open circuit test, first one is we can able to find the iron loss. Iron loss of the transformer. And next one is, so with this iron loss, what we can find in the sense, we can find the no load circuit. No load circuit of transformer. No load circuit of transformer. So for these two reasons, we are conducting the open circuit test. Okay, and this next one is how we conduct the open circuit test. Yes, so how we conduct the open circuit test? Tell me. Yes, the open circuit test is always conducted at the low voltage side, with the high voltage side kept open circuit. That means, yeah, OC test is conducting at LV side. That means HV side is open circuit. HV side is open circuit. HV side is open circuit. This is the first one. First point. Next, second one is, so now you need to apply the rated voltage at the LV side. That means here primary is LV side and secondary is HV side. Suppose I have the transformer. The rating of the transformer is 220 volts by 110 volts. So here for this transformer, so if I want to conduct the open circuit test, what I have to do? I need to give the voltage at 110 volts, and 220 volts side must be open circuit. 220 volts side must be open circuit. Okay. Yeah, the circuit is like this. Suppose for example, this is the transformer. So here I need to represent this as primary side is low voltage side, secondary side is high voltage side. So the secondary side is open circuit, 0 LV, 0 HV. Okay. Now here I want to find out the loss. To find out the power, I will connect one wattmeter. Yes, the main function of this wattmeter is to measure the power. To measure the power. And you have the dots, or which type of wattmeter I have to take. Whether it is UPF wattmeter or LPF wattmeter. As we are finding the magnetic losses, the magnetic loss is associated with the lagging power factor, because it is associated with the inductor, that is lagging power factor. So hence here I use LPF wattmeter. LPF wattmeter, and the ammeter is connected in series and voltmeter is connected in parallel. What is the purpose of this ammeter? The main purpose of this ammeter is to find out the no load current. So hence it is to be INR, and this is to be VNR, no load voltage. And this connection will be given to the auto transformer. It is single phase auto transformer. So the rating of the single phase auto transformer is 230 volts by 0 to 270 volts, like this. Okay. So here the input is single phase AC, 230 volts. Okay. So now what is the procedure? By changing the position of the auto transformer like this, this voltage value has to be increased. Whenever this voltage value, that is V0 is equal to, yes, V0 is equal to LV, then you can take the reading of LPF, that is wattmeter, and I0, V0. Yes, from this reading, so that means you can take like this: V0 value, I0 value, and W0 value. So here I can write the equation for this 3 as W0 is equal to V0 I0 cos pi 0. V0 I0 cos pi, where cos pi 0 is no load power factor. Cos pi 0 is no load power factor. So therefore we can find out the no load power factor as cos pi 0 is equal to W0 by V0 I0. No load power factor, you know. Yes, once you know the no load power factor and INR, now you can divide the I0 into two components, that is core component and magnetizing component in the no load circuit. So here I want to tell you what is no load circuit. No load circuit in the sense it is the combination of no load resistance, no load inductance. Yes, this is called R naught and this is called X naught. Okay, and here this current is I naught and this may be IC, core component of the no load current. IM or IMU, magnetizing component of the no load current. Okay. So how I can distribute these two, or how I can find these two, in the sense the mathematical expressions are there. That is, IC is equal to I naught cos pi naught and I mu is equal to I naught sin pi naught. So hence now if you see, I naught is equal to IC square plus I mu square under the root. IC square plus I mu square under the root. Okay. Now what is R naught? R naught is equal to V naught by IC and X naught is equal to V naught by I mu. This is how I got the no load circuit parameters as well as constant loss of the transformer from the open circuit test. Okay, from the open circuit test. Now let us see SC test, that is short circuit test. Short circuit test. Yes, short circuit test in the sense, here it is conducting at HV side and LV side is short circuit. LV side is short circuit. And this test is conducting to find out, to find out the copper loss of the transformer at full load condition. To find out the copper loss of transformer at full load. Copper loss of transformer at full load. Yes, so how we can do in the sense, so here also let me take the transformer. So here the primary is HV and the secondary is LV. Yes, this LV side is kept short circuit. LV side is short circuit. Now what we have to do? So here also the same process, but here we connect the UPF wattmeter, because the loss which is associated with the pure resistor, that we are going to find. So there, hence here I used to say UPF wattmeter has to be used. This is the wattmeter. Next, obviously, voltmeter. This voltmeter is, let me take VSC, ammeter, ISC, and this power, WSC. WSC is equal to copper loss at full load of the transformer. And here, as usual, one auto transformer is to be connected. Like this. This is the circuit diagram. So here what we have to do, so first we need to connect the circuit as per the diagram, and next second one is, by changing this auto transformer like this, you need to observe ISC. The value of ISC must be rated current of the transformer. Rated current of the transformer. So hence here you have to send the rated current, then you need to note down all this reading. So here what you have to do, VSC, ISC, WSC, where WSC is copper losses, which is given by WSC is equal to ISC square into RSC. This RSC is the equivalent resistance of the transformer referred to HV side. Referred to HV side. And from this you can able to find out the, yes, this WSC is full load copper loss. Yes, so from this value what we can do, what we have to do, can find out the equivalent circuit parameters of the transformer referred to HV side as VSC by ISC is equal to ZSC, and ZSC is equal to RSC square plus XSC square under the root. Okay. So from this you can also find XSC, as you know, ZSC and RSC. Okay, that is how you can able to find out the equivalent circuit parameters of the transformer and efficiency of the transformer with the losses. With the loss. Okay, and with this equivalent circuit parameters of the transformer, so we can also find the regulation of the transformer. This is very, very important. Okay, this is about testing of transformer. So thank you for watching this video. If you have any doubts or any suggestions, you can place in the comment box. Okay, so once again I am requesting you, kindly subscribe my channel, share my channel, and click on the bell button so for more videos. Thank you once again.